Welcome everyone. In today's lecture, we will study one of the most important software quality assurance techniques used in modern software engineering, that is static code analysis. Static analysis means examining the source code or the compiled code without actually executing the program. Unlike runtime testing, static analysis tools inspect the program logic and structure, encoding practices, and security vulnerabilities before the software runs. The major goals of it are to detect the bugs early, improve the code quality, increase the software reliability, enforce the coding standards, reduce the maintenance cost, and improve the security. Modern development teams heavily rely on automated static analysis tools because finding the defects earlier is significantly cheaper than fixing the bugs after deployment. The SpotBugs is an open source static analysis tool for Java. It is the modern successor of FindBugs. Originally, the project was called FindBugs, but after FindBugs became inactive, the community continued development under the new name that is SpotBugs. SpotBug analyzes the compiled Java bytecode rather than the raw source code. This means it examines the .class files and it detects the bug patterns and finds the suspicious coding practices. It also detects security vulnerabilities, identifies the concurrency problems, and detects the performance issues. Because it works on bytecode, SpotBugs can often discover issues that are difficult to identify using source-only analysis. Let's understand how SpotBugs works internally. So the process is step number one, the developer writes the Java source code, then the project is compiled to bytecode. SpotBug then analyzes the generated .class files, and next step it compares the bytecode patterns against its bug database. Warnings and reports are generated. This approach allows SpotBugs to detect the defects without executing the application. One extremely important concept is always compile before analysis, as SpotBug analyzes the compiled bytecode. If the source code changes but the project is not rebuilt, the bytecode becomes outdated, analysis results may become incorrect, warnings may reference old code, and developers may become confused. So therefore, always clean the code, rebuild the project, and then run the SpotBugs. So this ensures accurate analysis. Now let's see the warning structure of SpotBugs. So SpotBugs warning, also called a bug instance, may contain several attributes that help the developers to understand and fix potential defects in their code. Each issue detected by SpotBugs includes several important attributes. So these include bug pattern. A bug pattern is a category or type of problem that SpotBug has detected. It provides a short description and an explanation of the issue, including why it may be harmful and what kind of defect it represents. Purpose of bug pattern is to identify the nature of bug, and it explains the potential risks or consequences, and it helps the developers understand the underlying programming mistake and often suggest how the issue can be corrected. Bug pattern serves as a primary explanation of the warning and allow the developer to quickly recognize and address the detected issue. Now let's see the confidence levels. So SpotBug assigns a confidence rating to every warning. Confidence indicates how likely the detected issue is to be a real defect. Confidence levels are high, medium, and low. High confidence warnings are usually very reliable and should be fixed immediately. Low confidence warning may sometimes become, false positives. So this helps the teams to focus on the most critical issues first. Scariness ranking in SpotBugs. So SpotBugs also assigns a severity ranking called the Scariness rank. This estimates how dangerous the issue may be. Ranges are rank 1 to 4, that is scariest. Then rank 5 to 9, scary, rank 10 to 14, troubling, and rank 15 to 20, of concern. Lower number indicate more severe problems. For example, a potentially security vulnerability may receive rank 2, and a minor code style issue may receive rank 18. So this ranking system helps prioritize debugging and maintenance activities. SpotBugs organizes the warnings into categories. Major categories include correctness, security, performance, multi-threaded, correctness, bad practice, dodgy code, internationalization, experimental. Let us briefly understand each category. So number one is the correctness category. It detects the bugs that can make the program behave incorrectly, crash, or produces the wrong results. For example, null pointer dereference, using an object reference that may be null. Infinite recursion, a method repeatedly calls itself without stopping. Ignored return values, a method's result is not checked or used. Invalid typecasting, converting an object into an incompatible type. Incorrect comparison, comparing the values in a way that produces the wrong outcomes. Then is the security category. It identifies the coding weaknesses that attackers could exploit to compromise the system. So SQL injection, untrusted input is used directly in SQL queries. Hard-coded passwords, sensitive passwords are stored directly in source code. Path traversal, user input can access unauthorized file or directories. Unsafe deserialization, untrusted data is converted into objects without any validation. And finally, weak random number generation, so predictable random values may weaken the security. Then we have performance category that finds inefficient code that wastes the resources and slows down the application execution. Number one is unnecessary object creation, so creating objects that are not needed. Inefficient string concatenation, building strings in a slow or resource intensive way. Redundant computation, repeating the calculations that could be reused. Poor collection usage, using data structures inefficiently for the task. Then we have multi-threaded correctness category that detects the problem that occur when multiple threads access the shared data incorrectly. In this category we have race conditions, when multiple threads modify the data simultaneously causing unpredictable results. Inconsistent synchronization, shared resources are not protected consistently. Shared mutable state, multiple threads can change the same data object. Deadlock risk, threads may wait forever for resources held by each other. Then we have bad practice category. This highlights the risky coding habits that reduces the code quality and increases the maintenance effort. Ignoring exceptions, errors are caught but not properly handled. Using double equals to for string comparison, that is comparing object references instead of string contents. Empty catch blocks, so exceptions are silently ignored. Mutable static variables, that is shared global variables can be modified unexpectedly. Then dodgy code category, so this flags the suspicious or you can say confusing code that may hide the logical errors or bugs. In this category we may have useless conditions, that is the conditions that are always true or always false. Self-assignment, that is assigning a variable to itself with no effect. Duplicate branches, different code branches performing the same action. And impossible cast, for example converting an object to a type it can never be. Let's test your understanding with a quick scenario. A developer writes a query by directly inserting user input into the query string. Which SpotBugs category would most likely report this issue? The correct answer is B, that is security. Directly using user input in SQL queries can lead to SQL injection, one of the most common security vulnerabilities. SpotBugs reports such issues under the security category because attackers could exploit them to access or modify sensitive data. Next, a program repeatedly creates unnecessary objects inside a loop, causing the application to run slowly. So which SpotBugs category would detect this issue? The correct answer is performance. The unnecessary object creation wastes the memory and CPU resources, making the application less efficient. SpotBugs classifies these issues under the performance category. Two threads update the same bank account balance at the same time, producing different results each time the program runs. So which SpotBugs category is most relevant? Correct answer is multi-threaded correctness. This is classical race condition where multiple threads access the shared data without proper synchronization, leading to unpredictable behavior. Next, a method uses an object reference that may be null, causing the application to crash. Which SpotBugs category reports this problem? Answer is correctness. A potential null pointer dereference can cause the program to fail or produce incorrect results, making it a correctness issue. Here is one final challenge. A developer compares two Java strings using double equals instead of dot equals function. So which SpotBugs category would most likely report this issue? The correct answer is C, that is bad practice. So using double equals to compares object references rather than the actual string contents, which can lead to unexpected behavior. Although the code may compile and sometimes appear to work, it is considered a poor programming practice that reduces the code reliability and maintainability.